Computer. Hey, everybody. Welcome our team to Module 2. And this week we dive into a review of regression and ANOVA. And specifically, we get into how to apply regression in ANOVA using the R Studio and R software, which will be really great, kind of building on what we learned about last week, where we just sort of got familiar with using R and loading in data and things like that. So this is going to be a two-part video. So buckle in. Part one is just going to focus on ANOVA, and part two is going to focus on regression. So I have loaded up here the Module 2 R Markdown file, module MVS Module 2 handout.rmd. This is available on Canvas. And I'm going to be working through the code that you see here with some notes, and we'll hopefully learn some new stuff, which will be fun. So I'm going to start, as I always do, by loading in some relevant packages. And so I'm just going to push the play button here. We've talked about packages before, and so this should probably not be a surprise for you all. So I've loaded in the tidyverse. And the tidyverse is actually a collection of 8 different packages that are used for inputting, cleaning, coding, and manipulating, visualizing data, working with data of all kinds. It's a really versatile suite of tools. And so that's what these 8 packages are here with the check marks. And then, of course, we've loaded in the Haven package, which is a package for getting data in other formats into R. The format, again, I think this time is a statafile.dta. But again, you can load any type of data into R, SAS, SPSS, Excel, comma-separated variables, tab-separated variables, you name it. And that's all through the Haven package. Is a really easy way to do that. And then the HMISC package is just another useful tool for exploring data. HMISC stands for Harrell Miscellaneous. So Frank Harrell is a biostatistician who's developed a number of packages and has written a really good book on regression. So thanks to Frank, and we're going to use this package today. So let's start with our review of ANOVA. First thing we're going to do is read in our data. And just a quick review. These are sort of foundational concepts, so they're pretty important. So I'm going to create an object called systolic. This example comes from Stata. It's blood pressure data, but it could apply, as we'll see in a minute, this type of data, categorical data, could easily translate to situations in education and counseling, so on and so forth. So I'm going to create an object called systolic, and that's going to be my new data frame that I'm going to work with. And I'm going to create that object and assign it this name using the assignment operator, which is a little arrow that points at what the object is going to be called. And I'm going to use the read DTA function. So that's a function for reading in Stata data. And the name of the data set is systolic.dta. And my computer here is already pointed at the file location where that data set lives. Here's systolic.dta. So that'll save me a step. And then I'm going to view that data set. So it's going to pop open in a new window, and I'll get to look at it a little bit, see if there are labels and things like that. So I'm going to load that in. And sure enough, there we go. We get a new data set called systolic. It has only 58 observations of 3 variables. And I'm looking up here in my environment window. And then I can view this data set and kind of scroll around it and get a sense. So I've got a variable called drug, which is drug used, disease, which is patient's underlying disease, and then systolic, which is essentially a change. I think it's a change in blood pressure, like a pre-post, post minus pre kind of thing. So I think ideally we want to see that go down, or at least not increase very much. I should know more about this particular measure, but I don't. So there we go, there's systolic. All right, so I taught you about the glimpse command last week. Glimpse is a very useful tool from the tidyverse that allows you to get a quick look at the structure of the data. And there we go. It's a pretty simple data structure because there are only 3 variables. So we have 58 rows, that's 58 observations. I'm assuming that each observation is a different patient or person. I have 3 columns. I have drug, I have disease, and then systolic is actually the measure of change in blood pressure. A couple things that I notice right off the bat is that, first of all, drug and disease, if I'm interpreting them correctly, those are not numeric variables, but they are being treated as numeric right now by the software. That's what DBL stands for. It stands for double, or it's a type of numeric variable. So this is something I probably want to address when I go to clean this data, because if the data are truly categorical, R needs a different type of data label. It should be a factor variable and not a numeric variable. So I want to create some versions of those variables that are actually factors so that R knows appropriately what to do with those types of variables. And to do that, we're going to use a couple new tools from the tidyverse. I'm trying to remember. I don't think we used these last week. The first is a command called mutate. And whenever I see this, I think of X-Men, the X-Men, right? Mutants. So mutate just creates a new variable in a data set that is a function of an existing variable usually. So it's like a mutation of an existing variable that you perform. And it again comes from the dplyr package. And what we're going to do is we're going to create factor versions of these categorical variables. So we're going to keep the original. I always think it's a good idea to keep the original variables in there. It's tiny space. It doesn't hurt at all. But we're going to create new versions of the variables. For the drug variable, I'm going to create a variable called drug.fac. So it's a factor version of the drug variable. And to do that, I'm going to use this function called as_factor, another good one from the tidyverse. And I'm also going to do the same thing with this variable disease. So instead of the variable disease, I'm going to create a variable called disease.fac, which is a factor variable, basically taking that numeric variable and converting it into a factor. And then the last thing I'm going to do, just a little point, I actually make a copy of the whole data set when I do this. And this is a really good practice as if you're an analyst when you're working with data. A really good practice is to leave the original data untouched, which for us is this systolic, and then create a copy where it's the name of the data set dot clean. And that's the version of the data set that you work with, you run your models on, and so on and so forth. Because that way, if you discover an error, you don't have to go all the way back to the beginning and re-input the data. You just have to make an adjustment to this next step that I'm doing, which is where I'm actually cleaning my data. So from a workflow perspective, this makes a huge difference and can save you a lot of time in the long run. Plus, you might think of a new analysis that you want to do, and you can just make a few tweaks here and you're off and running. Okay, so I know there's a lot there, but this is a real kind of foundational skill here, which is taking a data set that you've inputted or input and then trying to clean it and manipulate it in a way that the variables all are what they need to be for your analysis. And so here's our command. So this is going to create a new data set called systolic.clean. And it's going to start with the systolic data set. So that's our starting point. And then notice that funny little character there. Oh my gosh, what the heck is that? Kind of looks like, I don't know, like a, I actually don't know what it looks like. It's called the pipe operator. This is called a pipe operator. And this is another tool that is associated with the tidyverse. And what the pipe operator means, I know it looks really weird and confusing. It just means then. Okay. So it means go to the next step. So start with this, then do this. You can put another one on the end afterwards, then do that, then do this other thing. The reason that we do this is because R is essentially a programming language. And so by default, R reads things from inside out. And so it can be very hard if you want to do a bunch of cleaning things to your data set. You have to nest them inside each other in a way that is not easy to read. Essentially, you're writing code from inside out. When as humans, right, we like to read from top down or left to right. And so this pipe operator helps you kind of break up different chunks in a readable way. This is a real development, at least for me as a coder. So I'm not naturally a coder. I don't have a background in computer science or anything. So for me, it made it a little more literate and allowed me to kind of see what was going on in a way that I might not otherwise. So anyway, we're going to start with the original data set. And then that's that pipe operator. And to do it, by the way, it's just the %, the forward caret greater than, and then the % again. And there's probably a shortcut for it too, but I usually just type it out. Okay, so then we're going to mutate our new function. And I usually put a decimal point here. I don't think it's strictly required, but I just want to remind myself that this is going back to the beginning. So this is where you would usually put the object that you're mutating, and we're really mutating this thing up here. So that's why I put the decimal point there, just to remind myself. And then a comma. And then my first new variable is called drug.fac. And that is going to be equal to the original variable drug converted to a factor using that function. And disease.fac is going to be this original variable disease converted to a factor. And then I close parentheses, put an extra parentheses here, and notice there's a little parentheses matching thing here. So when you put your cursor next to a parentheses, it shows you where the other one is. So there, it's up. This area right by mutate is highlighted because that's where that parentheses closes. Sometimes you run into having too many or too few. All right, and there we go. I run that, and look at this. So I now have a data set called systolic, but I have a new data set called systolic clean, which it has 58 observations and 5 variables because I've added 2 variables to the end. I've added 2 factor variables to the end there. And now let's take a look at this. I really like this command called describe, which comes from the HMISC package, because it does a nice job of separating your continuous variables and your categorical variables and kind of showing you what they all mean. So this is very similar, for example, to the describe function we learned about in the psych package. I prefer this one a little bit more. Some people really like the psych package. It's kind of a personal preference. So here's our original variable. So systolic.clean, 5 variables, 58 observations. Here's our variable drug, which we converted to a factor at the bottom. Here's the variable disease, same thing. Here's systolic. And notice systolic is continuous. And so we get a mean, which is about 19. We get percentiles all the way from basically 0 to 100. And we get the 5 lowest and 5 highest values. And then we get our new factor variables, which is great. So here's drug.fac. So this is that variable drug. So now you can see we have 4 different categories. So people were assigned to one of 4 different categories of drug. Think about like a trial. We have a lot of those now, right? Drug trials, vaccine trials, people are assigned to different categories. And so we have 15, 15, 12, and 16. And here are the proportions that those correspond to. And those people also have different underlying diseases. So this is people with different kinds of heart conditions, I think. So different types of cardiovascular disease. And so there are 3 different types of those. So 19, 19, and 20. So this is good because it shows us that these variables are being recognized as factors, right? They're not numeric. We're not getting means and standard deviations, which is not what we want. We just want the software to recognize that these people are in different groups, which is essentially the heart of what a categorical variable is. It's just a measure of group membership. Okay. All right, some other fun stuff. I always love a good visualization. You will learn that about me. For any analysis, I usually try to think about what is the way in which I can visualize this to make it clearer. And so for ANOVAs, box plots are really logical and fun, well, I think they're fun, maybe they're not fun, useful way of visualizing the data. So here is using the ggplot package, which we talked about last week. Here is how you create a box plot in R. So the command, the top line of the command is very similar. The command is ggplot. Here are your data. So the data here are systolic.clean, our new clean data set. And then we have our mapping function. So mapping equals aesthetic. And I think last week we didn't have an X because we were just making a histogram. And so, or sorry, we only had an X, I think, and we didn't have a Y, right? Because Y is just how many people are in each category. But here we're actually going to map an X and a Y because for a box plot, we need both. And so on the X-axis, we're going to have this variable drug.fac. And since it's a factor, ggplot already knows what to do with it. It knows this is not a continuous variable. This is actually groups. And so it needs to create a separate plot by group. And then on the Y-axis, we're going to have systolic, which is our measure of systolic blood pressure. So we're going to have little box plots for people in each group. And then the plus sign, and then the specific geome for a box plot is geome box plot, geome underscore box plot. And we don't need to make any modifications to that. We can just leave it as is. And then a plus sign. And then here I put in some fun labels. So distribution of change in blood pressure. For the Y-axis, change in systolic blood pressure. For the X-axis, this is the drug that we've used. So let's get a look at this. Ta-da! And here is our fun little box plot. A couple things to notice. By default, R puts in outliers. So those show up as dots. So here in group 1, for example, it looks like we only have one outlier. There's one person who had a negative change in systolic blood pressure. So their blood pressure went, I don't know, down or up or something, which was different than most of the people in the group who are up here. So just a quick reminder, dust this off, what this means. So the top and bottom of these, the whiskers, if you will, sometimes these are called box and whisker plots. So the whiskers of these are the observed maximum and minimum, not including outliers. Okay, so this is the observed maximum in the group. This is the observed minimum. The box represents the 25th and 75th percentiles, I believe. And the line here represents the, I believe it's the median value. So the line here is the median. The top and bottom of the box are the 25th and 75th percentile, and then the max and then the min, to try to give you a sense of what that all represents. So just looking at it, we see a pretty big difference, right? These two groups are associated with a bigger change in blood pressure than these two folks who are in these two groups. But it's a nice way to kind of just get a sense of what we're looking at. Alrighty. Okay. Whoops. Now, let's talk about running some ANOVAs, which is why we're here. So we learned a lot about cleaning and coding data. We learned about box plots, but now we need to figure out how to run an ANOVA. And since R is a statistics package, there's a nice built-in function for doing ANOVAs. It's the AOV command for analysis of variance. And so what I'm going to do, I am actually, and this is one thing that I really like about R, you can actually store models in your environment, just like you store data sets or plots or anything else. And so I'm actually going to give this analysis a name in case I want to come back to it later. So I'm going to call this ANOVA 1. And again, there's the assignment operator, and that this is going to be equal to, the command is AOV, analysis of variance. Your outcome goes first. So systolic is my outcome, and drug.fac is my categorical variable. And the data here are systolic.clean. So that's the whole command for an ANOVA. It's very, very simple. Outcome, tilde, the tilde sign, drug.fac, and or categorical variable. And then what data are you using? And then the summary function, by default, since you've assigned this to an object, it's not going to print anything for you. It's just going to store it in the object. But if you put summary and then ANOVA 1, it'll actually print out the results. And there we go. So it just ran our ANOVA. It's a very simple presentation, which I like. So we only have one factor. So we only have one sort of p-value and set of results, which is right here. So our categorical variable here corresponds to an F value of 9. That's pretty high, and a very, very small p-value. So this is actually in scientific notation. So it's 5.7 times 10 to the negative fifth. So it's 0.00005. Very small p-value, right? Typically, we think of anything below 0.05 as being statistically significant. And you even get the little significance codes here. So this is sort of associated with the lowest significance level, below 0.001. Okay, so what does that mean? Okay, so in an ANOVA, we're asking, does an outcome vary according to a categorical variable? Are there group differences on this outcome? And the answer to this is yes, based on this evidence. The sort of null hypothesis of our model is that there are no group differences. And so we reject that here because we have a significant p-value. And just by looking sort of descriptively, we kind of got a sense that there were group differences in blood pressure, just looking at the groups. We may want a little more information about this. We may want to sort of break this down and kind of figure out exactly what's going on. So to do this, I'll show you a cool trick you can do with the tidyverse. You can start with your systolic data set. You can arrange it or group it by this variable drug, or you could do drug.fac, either one, and then summarize it. And then we get summaries of the number of people in each group and the mean of blood pressure in each group. So this is kind of an equivalent to that visualization and helps kind of confirm what we found. So if you run this, notice here's drug 1, drug 2, drug 3, drug 4. Here are the number of people in each group, and here are the means. And so it makes sense, right? So group 3, the mean change in blood pressure was only 9 points. In group 1, it was all the way up to 26 points. So we're seeing some pretty big differences there. And so it kind of makes sense that we found a significant effect with our ANOVA. Okay, so the second phase of an ANOVA, first phase in ANOVA is, are there any differences? And that's what you get from this statistic right here in p-value. So it does look like there are statistically significant differences. So then when you're doing ANOVAs, your next step is to perform what's called a post hoc test. And if you remember back from 608, I know it might be a little fuzzy. There are a couple ways that are recommended. One is called the Bonferroni method. This is very conservative. It tends to not be significant, but if you do have significant differences, then they're pretty strong. You get that using this code here, pairwise t-test. And the outcome is systolic. The factor variable is systolic drug. And then the P adjustment method, that's what gives us Bonferroni. That's what the BONF means. So we get a set of mean comparisons. So this is pretty cool. So pairwise comparisons using t-tests with a pooled standard deviation. And basically, this is in the format of a little matrix, like a correlation matrix. And it gives you the comparisons between all the groups and the p-values that are associated with them. So here, for example, the comparison between group 1 and group 2, that is a very high p-value. So that difference is not significant. And we look at group 1 and group 2, that makes sense. The mean in group 1 was 26. The mean in group 2 is 25. Those two are almost equivalent. 1 compared to 3, though, we do have a significant difference, well below 0.05. That makes sense. Group 3 was very small. The comparison between 1 and 4 is also significant. And the comparison between 2 and 3 and 2 and 4 is also significant. But there is no difference between 3 and 4. So basically, when we're looking at this, 1 and 2 are not different from each other. 3 and 4 are not different from each other, but all the other comparisons are statistically significant. All right, so that's a Bonferroni. I keep doing that. I have a new mouse. Another method, which is not quite as conservative, is called Tukey's method, or Tukey's honestly significant difference, HSD. And again, there's a nice built-in command for that. It is Tukey HSD. And then for that one, you just need to put the name of the model in there. So if you've already run the model, it will calculate the rest. And so this is doing something very similar. It is comparing. I like this because it gives you the formula that you ran, and then it gives you all of the different pairings and combinations. This is very similar to what the output looks like in SPSS for this, although it's kind of in a more Cody type structure. So here's the comparison of 2 compared to 1. That is not significant. Those are the 2 high groups. 3 compared to 1 is, 4 compared to 1 is, 2 compared to 3 is significant, and 4 compared to 2 is, 4 compared to 3 is not. So again, these are the only 2 that are not significant. And these are confidence intervals for the difference between the 2 groups. So for example, for 1 compared to 2, the confidence interval, 95% confidence interval goes from -11 to +10. So if the confidence interval contains 0, that difference is not significant. If the confidence interval does not contain 0, though, the difference is. So here, 3 compared to 1, the interval goes from -28 to -6. So some people don't like p-values, some people prefer confidence intervals, and so that this particular method gives you both. You can also calculate some effect sizes. Hopefully this is bringing back some memories from your 608 days. So first step, run the ANOVA. Second step, look for, if you have a significant ANOVA, look for group differences. Third step, calculate some effect sizes. The standard effect size is what's called an eta squared, but the more preferred effect size nowadays is called an omega squared. You can get either one. They're both found in this package called effect size. So you may need to download this if you don't have it already. I already have it. And once you have it, you can just type in eta squared and the name of your variable, and partial equals false in this case, since we only have one factor. When we do a two-way ANOVA, we will want partial eta squared and partial omega squared. Same thing with omega squared. We get the same estimate. Basically, what you find is omega squared is a little more conservative. It's a little bit lower. But these are both really big effect sizes. The effect size rules, I forget the rules. It's like, I think it's like 0.01 to 0.05 is small. 0.05 to 0.1 is medium, and anything above 0.1 is considered large. Those are very loose rules of thumb, though, and they're a little bit different from like Cohen's D, for example, which is another type of effect size. But so that's how that works. And yeah, so that's one-way ANOVA. Okay. You can also do two-way ANOVAs in R. So just a quick recap, two-way ANOVA just means you have a second categorical variable. So in the previous model, we had drug as our only categorical variable, which drug people were assigned to. But you can also have a second condition. In this case, we know what type of disease people have. And so we can actually look at both of those things simultaneously, both drug and disease. And I know I mentioned vaccines earlier, but this is kind of a situation where this might actually be kind of useful. So we know, for example, that there are a bunch of different vaccines, right? So people may sort of randomly be assigned to receive different types of vaccine. But we also know there are different variants of the coronavirus. And so this actually might be an analysis that would be kind of beneficial if we had the data to understand the extent to which these drugs are effective for people with different underlying conditions or slightly different mutations. In this case, do the drugs work equally well for people with different types of cardiovascular disease? That's what we're looking at in this case, but just a connection to kind of what's going on. So we can make a nice two-way plot here. Again, same command, ggplot, data, mapping. All I did here, notice, the only thing I've changed, I added this command color. And so what this is going to do is this is going to split out that nice plot we had before. And for each drug group, I'm going to have different groups according to disease that are going to be arranged by color. And so we can just run this and have a look here. And so now we have a two-way plot. And notice we now have, so here's everyone in drug group 1. So in drug group 1, we have people who had 3 underlying categories of disease. So here's category 1, category 2, category 3, and notice they're now split out. And here's drug group 2, category 1, category 2, category 3, so on and so forth. We still get outliers by group, so a few outliers to pay attention to. Otherwise, it looks very similar. So this is kind of a classic two-way ANOVA plot that kind of shows you the distribution within each group and also by the second factor variable. And so then the command for a two-way ANOVA is very similar. Again, it's AOV, analysis of variance, and I'm going to call this thing ANOVA 2. And our outcome is systolic. Our first variable is drug.fac. Our second variable is disease.fac. And notice we just have plus signs in between them. And then we have the interaction of the two, which we just notate with a little star, excuse me, an asterisk. So we have drug.fac times disease.fac. And this is very standard. We do the same thing. This is the default in SPSS, is to model the interaction between these two. We want to know if the impact of one categorical variable is associated with the impact of another. And so that's the way to model it. And then our data, again, is systolic.clean. And here's our summary. So we run that. And now we have a few different estimates. We have an estimate for drug.fac, and that is still statistically significant. An estimate for disease, that is not statistically significant. The p-value is 0.162. And an estimate for the interaction, and the p-value there is 0.396. So we don't have an interaction and we don't have an effect by disease. So the groups don't appear to differ by disease in terms of their blood pressure. And we don't seem to have an interaction between the two. Again, we can get effect sizes from this using omega squared. And now we do ask for the partial because we have more than one factor in our model. And we can also get Tukey's HSD here. Notice the omega squared is very, very large for a drug and pretty small for to non-existent for the others. And then our Tukey's HSD looks kind of wild because here we get every comparison by drug, every comparison by disease with p-values, and notice none of those are significant. And then every comparison by drug and disease, which is pretty wild. That's probably more information than we need, but we do get all those comparisons. Okay. All right. We made it, folks, through the ANOVA section. A lot to cover here. Just to recap, we started with some data cleaning and coding things. We learned about the mutate function, and how to create a factor variable, which is a very important skill, and how to create a clean version of a data set. We learned a new tool for describing our data set, how to visualize it, and then how to run both one-way and two-way ANOVAs, measure effect size, and do post-hoc testing. So lots of fun stuff there. Hope you found it useful. In part 2, we'll dive into regression. And we'll go from there. Thanks.